Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are learning the course that is named as Introduction to Statistics, and we are following the book of Anderson and Sweeney. The book name is Statistics for Business and Economics. Today, we are going to learn distribution. The one probability distribution named after the French mathematician Simon Denis Poisson. It is another important probability distribution for the discrete random variable that has a large number of applications. Suppose that a washing machine and a laundry break down on an average of the probability of exactly 2 breakdowns during the next month. This is an example of a Poisson probability distribution where each time is called an occurrence is in Poisson occurrence. The Poisson is applied to experiments with the random and independent occurrences. The occurrences are random in the sense that they do not follow any pattern, and hence they are unpredictable. Independence of occurrences means that occurrence of an event does not influence the successive occurrence of that event. The occurrences are always considered with respect to an interval. In the example of the washing machine, the interval is 1 minute. Sorry, the interval is 1 month because we suppose that a washing machine in the laundry breaks down an average of 3 times in a month. So the interval is 1 month. Now, the interval may be a time interval, a space interval, or a volume interval. The actual number of occurrences within an interval is random and independent. If the average number of occurrences for a given interval is known, then by using the Poisson probability distribution, we can compute the probability of a certain number of occurrences in that interval. So we have three conditions that must be satisfied to apply the Poisson probability distribution. The first condition is that x is a discrete random variable. The second condition is the occurrences are random. The third condition is the occurrences are independent. So we studied three conditions that need to be satisfied to apply the Poisson probability distribution. These three conditions are: x is a discrete random variable, the occurrences are random, and the occurrences are independent. Now we will consider some more real life examples uh, to see how Poisson probability distribution can be applied. Consider the number of telemarketing phone calls received by Abdullah during a given day. Listen again. Consider the number of telemarketing phone calls received by Mr. Abdullah during a given day. Now, in this example, the receiving of a telemarketing phone call by Mr. Abdullah is called an occurrence. The interval is 1 day, and the occurrences are random. That is, there is no specified time for such a phone call to come in. The total number of telemarketing phone calls received by Mr. Abdullah during a given day may be 0, 1, 2, 3, 4, and so on. Now these numbers are discrete. The independence of occurrence in this example means that the marketing phone calls are received individually and none of two or more of these phone calls are related. Now consider the second example. Now consider yourself be as a quality manager in a firm and you are looking for the number of defective items in the next 100 items manufactured on a machine. Now in this case, the interval is a volume interval. That means the 100 items. The occurrences, that means the number of defective items, are random and discrete because there may be 0, 1, 2, 3 up to 100 defective items in 100 items. We can assume the occurrence of defective items to be independent of one another. The third example is consider the number of defects in a 5-foot long iron rod. The interval in this example is a space interval, that is 5 feet. The occurrence, that is defects, are random because there may be any number of defects in a 5-foot iron rod. We can assume that these defects are independent of one another. Some of the other examples may be the number of accidents that occur on a given highway during a 1 week period, the number of customers entering a grocery store during a 1 hour interval, the number of television sets sold at a department store during a given week. These are some of the examples. The other examples may be the number of arrivals at a car wash in 1 hour, the number of repairs needed in 10 miles of highway, or the number of leaks in 100 miles of pipeline. The Poisson probability function is defined, that is, f of x equal to mu power x e power minus mu divided by x factorial, where f of x is the probability of x occurrences in an interval. Mu is the expected value or mean number of occurrences in an interval, and we have E is equal to 2.71828. For the Poisson probability distribution, the x is a discrete random variable indicated the number of occurrences in the interval. Since there is no stated upper limit For the number of occurrences, the probability function f of x is applicable for values x is equal to 0, 1, 2, up to so on without limit. So in this Poisson probability function, we have only one parameter, that is mu. Always remember, the parameters are those values which help us to solve the equation. Like in binomial distribution, we have two parameters. These are n and p. And now in Poisson probability function, that is f of x is equal to mu power x e power minus mu divided by x factorial. In this equation, there is only one parameter, that is mu, the mean. If we know the value of mean, we can solve the equation. Because x is the random variable, we can just put the value of x and get the desired results. Let's look into an example. Suppose that we are interested in the number of arrivals at the drive-up teller window of a bank during a 15-minute period on weekday mornings. If we can assume that the probability of a car arriving is the same for any two time periods of equal length, and that the arrival or non-arrival of a car in any time period is independent of the arrival or non-arrival in any other time period. The Poisson probability function is applicable. Suppose these assumptions are satisfied and an analysis of historical data shows that the average number of cars arriving in a 15-minute period of time is 10. In this case, the following probability function applies because we know that the average number of cars arriving in 15-minute period of time is 10. So we can place the value of mu as 10. So we have probability function as f of x that is equal to 10 power x e power minus 10 divided by x factorial. Now the random variable here is x, and x is the number of cars arriving in any 15-minute period. If management wanted to know the probability of exactly 5 arrivals in 15 minutes, we would set x is equal to 5 and thus obtain probability of exactly 5 arrivals in 15 minutes. Now we have the value of x as 5. So f of 5 is equal to, now you just need to place the value of x as 5 where you have x in the equation, that is 10 power 5 e power minus 10 divided by 5 factorial, that is equal to 0.0378. Although this probability was determined by evaluating the probability function with mu is equal to 10 and x is equal to 5. Well, it is often easier to refer to a table for the Poisson distribution. The table provides probabilities for specific values of x and mu. For example, look at the table in the above example. We have the value of mu that is equal to x. The value of mu is 10 and the value of x is 5. The bold values are the mean values like 9.1, 9.2, 9.3, 9.4, 9.5, 9.6, 9.7, 9.8, 9.9 and 10. These values are for the mean values and x is the left hand first column is the values of x. Now we have the value of mean is 10. So we'll look at into the column of 10 and x as 5. So we come down, look at the last table in the column of 10 and state from 5 we see the value of 0.0378 as the bold value. This is our probability value. ठीक है जी, आप लोग करेंगे क्या? आप लोग करेंगे ये कि आप लोग मीन के पहले मीन के टेबल के ऊपर देखेंगे कि आपको मीन की वैल्यू कौन सी है, ठीक है? तो आपने देखा कि आपका मीन की वैल्यू 10 है, तो आप 10 वाले कॉलम में आ जाएंगे, ठीक है? फिर आप वहाँ पर देखेंगे कि आपकी एक्स की वैल्यू क्या है। आपकी जो एक्स की वैल्यू होगी, ठीक है, उसको स्टेट आप देखेंगे मीन के टेबल में, जहाँ पे आपकी मीन की वैल्यू होगी। जो उसके सामने वाली वैल्यू होगी वो आपकी प्रोबेबिलिटी की वैल्यू होगी। तो एक तरीकाकार तो यह है कि आप फार्मूले से कैलकुलेट कर लें, ठीक है, वो भी ठीक है। दूसरा तरीका यह है कि आप डायरेक्ट जो है वो टेबल से कैलकुलेट कर लें, ठीक है। दोनों तरीके ही ठीक है। जो आपको इजी लगे. So one of the very important property of Poisson distribution is that its mean and variance are equal. For example, the mean of in the preceding example, the mean of the Poisson distribution is 10 arrivals per 15-minute period. A property of the Poisson distribution is that mean of the distribution and the variance of the distribution are equal. Thus, the variance for the number of arrivals during 15-minute period is sigma scale that is equal to 10. The variance and means in Poisson distribution are equal and the standard deviation is positive square root of 10 that is equal to 3.16. Now, in our illustration involves a 15-minute period, but other time periods can be used. Suppose we want to compute the probability of one arrival in a 3 minute because 10 is the expected number of arrivals in a 15-minute period. We see that 10 by 15 is equal to 2 by 3 is the expected number of arrivals in a 1 minute period, and that 2 by 3 multiplied by 3 that is equal to 2 is the expected number of arrivals in a 3 minute period. Thus, the probability of X arrivals in a 3 minute period with mu is equal to 2 is given by the following Poisson probability function. As we have computed the probability for 3 minutes, you can also compute the probability of 6 minutes, 5 minutes, 10 minutes, 12 minutes, okay, by using the same calculation. That is f of x is equal to 2 power x e power minus 2 divided by x factorial. Now let us illustrate any application not involving time intervals in which Poisson distribution is useful. Suppose we are concerned with the occurrence of major defects in a highway 1 month after resurfacing. We'll assume that the probability of a defect is the same for any two highway intervals of equal length, and that the occurrence or non-occurrence of a defect is any one interval is independent of the occurrence or non-occurrence of a defect in any other interval. Hence, the Poisson distribution can be applied. Suppose we learn that major defects 1 month after resurfacing occur at an average rate of 2 per mile. Let us find the probability of no major defects in a particular 3 miles section of the highway. Because we are interested in an interval with a length of 3 miles, mu is equal to 2 defects per mile multiplied by 3 miles, that is equal to 6, represents the expected number of major defects over the 3-mile section of highway. Now using the equation of Poisson probability function, the probability of no major defect, that is f of 0, is equal to 6 power 0 e power minus 6 divided by 0 factorial, that is equal to 0.0025. That thus it is unlikely that no major defects will occur in the 3-mile section. In fact, this example indicates a 1 minus 0.0025, that is equal to 0.9975 probability of at least one major defect in the 3-mile highway section. So now let's consider one question number 39. Consider a Poisson distribution with a mean of 2 occurrences per time minute. So your mu is 2. Part A. Write the appropriate Poisson probability function. So f of x is equal to 2 power x e power minus 2 divided by x factorial. That is part A. What is the expected number of occurrences in 3 time period? We know that the mean of 2 occurrences per time period. So when we have 3 time periods, that means our mean is equal to 6. So write the appropriate Poisson, part C, write the appropriate Poisson probability function to determine the probability of x occurrences in 3 time period. That is f of x is equal to 6 power x e power minus 6 divided by x factorial. Part D. Compute the probability of 2 occurrences in one time period. So remember, we will use the one time period probability, Poisson probability function. That means in one time period, the value of mu is 2. So now we need to compute f of 2, that is 2 power 2 e power minus 2 divided by 2 factorial, that is equal to 0.2706. Part E. Compute the probability of 6 occurrences in 3 time period. Now we will use the Poisson probability function for the 3 time period. That means our mu or mean is 6 now, and we are going to compute f of 6, that is equal to f of 6 is equal to 6 power 6 e power minus 6 divided by 6 factorial, that is equal to 0.1606. And part F. Compute the probability of 5 occurrences in 2 time period. So we first compute 2 time period. We know that our mean of 2 occurrences per time period. Now we have 2 time period. That means our mu becomes 4, and we are going to compute f of 5. f of 5 is equal to 4 power 5 e power minus 4 divided by 5 factorial, that is equal to 0.1563. Okay, so this is question number 39. Question number 40, 41, 42, 43, 44, 45, These are on the same lines. You can practice it by yourself. If you find any problem, then we can discuss it in the class. Okay? Thank you for listening the lecture. Have a nice day.